Okay, welcome back everyone. Now since we've seen how to write kernels quite a bit now, written an initialization kernel, the heat equation kernel, it is time to see how all of these things are actually called and how do we define buffers and how do we define our accelerators, things like this. So I was talking to another colleague of mine. So I was trying to explain that, this is the code you need to set up the simulation, and it's a lot more like boilerplate because this is the code which is really defining the things you need to run your kernels. And what we've done till now is what would be the core of your science case. And now we look at the setup.
Yeah, up to now we focused on portable kernel implementations. This section will be about host code, namely selecting the devices to run the codes and preparing and passing data to kernels, copying back the data from GPU or from accelerator to the host. Yeah, these will be main topics. Initially, I would like to talk about some alpaka concepts. For example, the accelerator, we need to select an accelerator type to use a specific backend, to use a specific accelerator. On host, accelerator is a meta parameter for choosing correct physical device. But inside kernel, as you have seen, inside kernel, it is an instance and contains thread state, provides access to alpaka device side API. And we have a concept, we have another alpaka data structure called device. And the device types and device instances can be derived from the accelerator type, because accelerator type actually a general definition of the device who is going to be used for parallelization. Host types and host instances are also needed. If we want to create a buffer at the host, we need to use host device, and if we want to use we want to create a buffer, we need to use the accelerator device, of course. In detail, accelerator actually hides hardware specific behind alpaka's abstract API. Let me show it. Yeah. On host, accelerator is a type, as I told you. Inside the kernel, accelerator provides the means to access to indices, as you have already used in the getIDX function. And getIDX should know what is the index, and this index should be get from by using the ACC. ACC is also used. I mean, the accelerator instance is used also in creating shared memory blocks, and it is also used for synchronization in sync block threads. And it is also used for many functions, many functions like square root or atomics, or creating a random number, because alpaka provides abstract way of or portable way of calling these specific functions. Alpaka has its own functions to use them in a portable manner. Therefore, ACC variable is used in these functions. Alpaka buffer is a multidimensional dynamic container, and contains memory address, extent, data type, and the device. Device is important because normally in C++ or in any language, there are many, of course, data structures which are multidimensional containers, but they don't have the device. For example, when we allocate buffer in the memory, we are giving the buffer type, the index type, and the device, together with the size of the buffer. If extent is a 2-item array, which is an alpaka vector, then this will be a 2-dimensional array, and but the device will be the CPU. And if another device is used, like a GPU device, then the buffer will be allocated at the GPU. And this is important. You can easily copy two buffers from one device to another device. Always memcopy copies from the second to the first buffer given. Here the second buffer is the CPU, and this copy is copying from the CPU to GPU. And as you see, we don't define the direction, or which one is the device or which one is the host. We are just directly copying it. And we don't define the size. We don't give the size of the buffer. For example, in CUDA memcopy, you need to use the size of the buffer in bytes, yes, and the direction of the copy. But alpaka memcopy is easier in that sense. Alpaka vector is a static 1D array. We have used it. Why what means static? The size is defined in the compile time, and size is given as a type, as we have done before. And this is the data type of the vector. And alpaka view is important. It is a non-owning view of an already allocated memory. If you have a STL vector, for example, or any other container, contiguous container, you can convert it to an alpaka view, then use it like any other buffer in these memcopies or for some other alpaka functions. Therefore, it increases the portability of the code.
Question?
Yes.
About this one, was this GPU view? What is it?
Yeah, I will talk about queues
Later, okay.
just
Okay.
2 slides later. Yeah. Yeah. Okay. I would like to talk about getValidVector function. GetValidVector function actually gives a valid work division to be used to run the kernel. And what exactly get-valid-work-to do? It takes a 2D thread domain, and we define a general domain, and get-valid-work-to actually finds the block size, which is valid for the hardware, and which is also which takes care of hardware limits. Not only hardware limits, but also it uses kernel parameters, not only the kernel and kernel parameters, to get information about the number of registers, for example, the kernel is using, whether the number of registers used by the kernel, can be handled by this block size. Therefore, using get-valid-work-to is an important feature of alpaka, which is also independent of the accelerator. It just creates a work division for us. Yeah, the extent of this 2D, let's say, thread domain is given as a vector with 2 elements, and elements per thread is also given. Usually we take 1, but it could be different. Yeah, of course, instead of get-valid-work-to, work-to can be defined by the user, and we define 3 vectors, which shows how many blocks in the grid we have. We have m by n blocks, actually. M rows of blocks and n columns of blocks exist in the grid. Then each block has a size 32 by 32, and the element extent and thread element extent is also a 2D 2-item vector. Yeah, then we can just create a variable called workdiv2d, which has 3 vectors, and there are also 1D or 3D definitions. It's also possible to create 1D or 3D workdivs. Yeah, alpaka queue is a queue of tasks, actually, used for synchronization of tasks like memcopy or kernel execution. As you may have noticed, in every memcopy or exec, we use a queue. Queue is used for synchronization because we cannot do every task at the accelerator device synchronously. There should be a kind of an order, a synchronization, and synchronization of tasks between host and device or between many devices can also be achieved by using queue. If a queue is non-blocking, the caller or the host is not blocked. For example, if our queue is non-blocking, when we call the memcopy and if we don't wait here, then we immediately call the exec. Then the memcopy will not block the host, and exec will be called just after the memcopy. But there's a wait. Why there's a wait? Because we want to make sure that all the buffer from the host to the device, to the ACC device, copied and the operation finished, then we can run the kernel. Therefore, therefore we added a wait here. Actually, it is not necessary here because a queue is always FIFO, and it is always ordered. If there were more than one queues, for example, that could have been waiting, could have been important, but it's not needed actually here. Yeah. Non-blocking queues can run in parallel. For example, I can show you if you have a single queue, whether it is blocking or non-blocking, every operation we assigned like memcopy exec to the queue, then they will be executed in order. One of them is going to finish, the other is going to start, whether it is a blocking or non-blocking queue. But let's assume that we have blocking queues. We initially did a memcopy using the first blocking queue. Then we did a memcopy using the second blocking queue of the same accelerator. Then, of course, since they are blocking queues, the first one is going to run and it's going to block the host. Then, after the first task finished, then the second one is going to run. Then we call in the code a kernel execution. Then we call immediately kernel execution for the second queue. But before finishing the first kernel execution, host will be blocked. Then our second call will not be activated because queues are blocking queues. Blocking queues can be used if, for example, we want to be sure that two different operations finished before a kernel execution here. But if you want to optimize ACC usage, we can use two non-blocking queues, and we can just run a copy, then kernel execution, then another copy at another ACC, another copy at another queue of the same ACC. Then, of course, since this one in the queue everything is in order, initially the copy is going to be done, then kernel is going to be started. Then, since this is a non-blocking queue, our call, copy call, will also be started. Therefore, this is good for increasing the performance. We are showing here, we have two GPU queues, and initially we do a memcopy, and we wait. So that this memcopy is finished. We are here now. Then we are running memcopy and exec from two different non-blocking queues. They immediately start, and then we wait for the results of both of them, so that at the end we will have both of them have finished and we can maybe do something else. The code only shows up to this point. Yeah, this is the concept of queue. It is very similar to concept of stream in CUDA, but alpaka is transparent. In CUDA, there is a default stream which is embedded to the code, but alpaka is transparent. Therefore, we explicitly use here for each operation a queue, and any task can be any task can be converted to any operation at ACC can be converted to a task. Normally we call exec, for example, execute the kernel or memcopy. These could be converted to different tasks And tasks can be assigned. That's also possible. And for example, with create task kernel, we create a task which runs a kernel, or with create task memcopy, we just create a memcopy task. Enqueue function can be used to execute the task at a queue. It's like calling exec or calling memcopy, but this is just explicit operation. Wait, as you have already seen, can be used to make queue finish all tasks and queue it. And wait can make a queue wait another queue to complete all queue operations. And we can check if a queue is empty or not, if there is any task remaining in the queue or not. And the alpaka is also an event data structure. Events can also be enqueued, and another queue can ask for whether the queue with an event reached actually to that event. I mean, this is also a synchronization. And previous scenarios, already we have discussed the previous scenarios, but event, for example, here the second kernel execution waits the event from the from another queue of the same accelerator. And different scenarios are possible to use efficiently GPUs using queues. Now we can go over kernel execution and copying data. Again, initially we create a queue using a specific device, not the accelerator, but the device derived from the accelerator. And this is done in the host code. We haven't called yet the kernel. Then allocation of buffer is also using the device, and the size of the buffer is given. It's an alpaka vector. And execution of the kernel again needs a queue, and kernel work division is given, and the kernel instance is given. Then the kernel arguments are also used in the exec function. Copying, copying, this is the memcopy. Again, as you see, it is an ACC operation, and ACCQ is used for the memcopy operation so that we can synchronize device copy operations.
Yes, question.
What exactly is the difference between which is essentially creating a task to run a kernel first and then enqueuing that task to the queue, in contrast to using the execute kernel work division on a queue?
It is the same. If you check exec function. Okay, the question is that what is the difference between calling exec function to run a kernel and creating a task to run the kernel and enqueuing the task? What is the difference between using the exec function or enqueuing the exec task? It is the same actually. Exec function also creates a task kernel, then enqueues it, but it is a simpler way of creating a kernel task and enqueuing.
let me quickly add, in rare situations, it might be that the creation of the task itself, or the task itself, is a heavy object, and in that case, you might want to cache it for reuse.
Yeah. Oh, good point. Thank you. Actually, I was planning to explain MDSpan, then we can move on to MDSpan example.
Let's
Okay.
go through this.
Okay.
So, okay, that was a lot of theory, but this is what the core of alpaka is. This is what makes the kernels tick. So let's go over this only as a hands-on. I would recommend using the cheat sheet extensively. This is why it's there. You can see almost all of what Mehmet just explained is mentioned already in the cheat sheet. And don't worry if you don't get it all at once right now. We will go over it again. So, apologies for the people online especially.